Hi, good morning, good afternoon, good evening. My name is Rory Fulger, and I am an instructional designer and technologist at Wolfram Research, and also the camp director for the Wolfram Middle School and High School summer camps. So today we are going to talk to some of our amazing students who've attended the summer programs this summer, and we're going to hear some about their projects. But I just wanted to start out with a little bit of an introduction as to kind of what camp is and what these students have been doing. So we run two camps at Wolfram. Our middle school summer camp, which was the first time that we've run it this year. So it's a brand new camp where we had girls and other non-male students attend for a week, getting to know Wolfram language. They're the kind of younger students, though they were 11 to 13 years old, and they had a really good time kind of going through the introductory materials and doing lots of active learning and research for themselves. And then we run the high school summer camp, which is a 3-week program where students aged roughly 14 to roughly 17 join us for 3 whole weeks to not only learn a whole load of Wolfram language skills, but also to develop their computational thinking skills and to do a undergraduate level project, which they do with the help of a mentor in small groups. They all do their own project, and they do some amazing things in all kinds of fields, ranging from politics to physics to math, and it's all very exciting. I've noticed that in the audience we have a couple of our high school summer camp alumni, which is really exciting to see, and a couple of our mentors from camp, people who've been mentors in the last few years. So that's really exciting. Welcome so much, and thank you for everybody who we have not met before for coming to listen to hear these kids talk about their projects. So what we're going to do today is we're going to hear from these 3 students for about 10 to 15 minutes each, and then after each of them presents their project, you'll have the opportunity to ask questions, and you can do that either by putting up your hand or by typing into the chat, either on Pathable or on Zoom. I'm watching both, and you'll have the opportunity to ask them some questions at the end of each student's little presentation, and then also to ask at the end any questions that you have about the summer camp. Okay, so we're going to start with Fiona, who is one of our youngest students. So she attended the middle school summer camp earlier in the summer, and then was interested and learned quickly enough to move straight into the high school summer camp a few weeks later. And she's done a really awesome project on the kind of math and image processing behind flowers. So I'm going to hand over to Fiona to talk for 10-15 minutes about her project.
So, hi, my name is Fiona Law, and my project was on picking out spirals in the images of flowers. So in this specific project, there was an interest that I had. So in my free time, I like to go outside and take pictures as a hobby, and I like to go take pictures of flowers. And so in plants, there's a common pattern, which is the Fibonacci sequence. So this is what my project focused on. And using generated data, I compared the ideal ratio of the spiral of the Fibonacci sequence and a picture in order to see how the growth angle compared to my data. So first, I cropped the image so that it would focus only on the middle or the anther of the flower. And using color separate, I separated the colors so that it became gray and black. And then once I did that, I changed it so that it was black and white. And then I used image multiply to combine these two pictures so that the background was black and the middle part of the flower was gray. And you can see the individual parts of the anther in the gray area. And using morphological binaries, I combined these two images so that the actual anther part was also black and white. And then from here, I colorized that image so that it was easier to visualize each individual part of the anther. So then I converted the points from Cartesian coordinates to polar coordinates. So I did this by finding the center of each anther point, and then I got the Cartesian points so that it became polar coordinates, and coordinate transform was what I used in order to transform between these two different coordinate systems. And then after that, my mentor and I used a formula from the New Kind of Science website by Stephen Wolfram that gave a formula that would show the flower spiral function. And it showed that the ratio angle of the Fibonacci sequence was approximately 137.5 degrees. And here the formula is what the function is. And using this is an example of what it would do. So there are 5 different points, and the growth angle is 137.25 degrees between each spiral. And then once we did that, we used we named golden points so that it would find the ideal ratio so that we could compare that to my ideal ratio or to my own data so that we could compare them both on a graph. So once I had the data from the golden ratio and the data from my own image, I plotted both points onto a graph. So the black dots would represent the ideal generated data and the red dots would represent my data. So as shown in the graph, the red dots are pretty similar to the location of the black dots, except for this area, which is pretty hard to find an image because the black dots would represent the ideal ratio. And since the image that I chose wasn't exactly perfect due to different circumstances like lighting and the angle of the picture, there's some missing dots, but overall the red dots and black dots had a pretty similar location. So in conclusion, the constant theme in my project was that there were many different factors that came up that had to be considered since the camera angle wasn't perfect and the lighting of the image wasn't perfect. So the generated data was pretty similar to the ideal ratio of the Fibonacci sequence. And in the future, I would like to test the same method on different plants and flowers since the Fibonacci sequence can be found in different areas of nature as well. Thank you.
Awesome. Thank you, Fiona. I really appreciate that presentation. Does anybody have any questions for Fiona? While people are maybe typing, what was the most kind of challenging part of your project?
The most challenging part was probably finding the exact method I would use in order to get my final results.
Totally. Yeah, that can be hard. What do you think was the coolest thing you learned?
The coolest thing I learned was that the Fibonacci sequence is actually really similar to like any other flower, and the ideal data was really close to the image that was my generated data.
Love that. Awesome. Okay, if anybody has any questions, feel free to raise your hand or put them in the chat. Just another 5 seconds for that. Okay, wonderful. Thank you so much, Fiona. That was really cool. I love your project. Amazing. Okay, our next student is Rohan. Oh, wait, here we go. Roman has a question. Does your partitioning and colorizing function work on non-flower images? As long as the main part is yellow.
Yeah, so before I started my project, I played around with different functions, and the colorizing function does work on different images as well.
It's awesome. And we have another question asking if this was your first time using Wolfram language.
So as Rory said earlier, before this project, I also participated in the middle school camp, and that was when I basically had my introduction to Wolfram. So it was not my first time using Wolfram language.
You've been using it all the way since June. Yeah. It's really cool how quickly our students like really pick up advanced Wolfram language stuff. It's very cool. Great. And you have a great work comment in the chat. Okay, awesome. So our next student is Rohan. And Rohan attended our high school summer camp, sorry, and did a very cool project on pi calculus, which is a field that, well, a concept that I had not heard of before camp, and so really exciting to learn about that alongside him. So Rohan, feel free to share your screen.
Yeah, so as Rory said, my name is Rohan. I'm an 11th grader. I'm really interested in computer science, so I was really excited to be part of this year's summer camp, and I'm going to share with you my project, which was about studying the pi calculus. So like Rory said, the pi calculus isn't something that's super well known, but something that is a little bit more well known is the Lambda Calculus. And the Lambda Calculus is the simplest sort of functional sequential programming language you can have. So the pi calculus tries to be the same thing, except it tries to be the simplest functional concurrent programming language you can have. And it's probably good to talk about the difference between concurrent and parallel programming here, because I know it was something I was originally confused with when I was trying to learn more about this. But the pi calculus only deals with concurrent programs. And the main difference between concurrent programs and parallel programs is that a concurrent program has all these tasks it wants to do, and each of those tasks are competing to be done. They're basically competing for time on your processor or on your computer, which you only have one of. Parallel programs, however, there's multiple processors, multiple computers, and so we can actually run two different tasks at the same time. But in concurrent programs, we still are only able to run one task at the same time. And even though we're limited in this sense, concurrency is still a pretty powerful paradigm we can use to model all these sorts of interactions. For example, clients and servers can be modeled as a concurrent process. Even certain biological reactions in our body can be modeled as concurrent processes. So it's a pretty powerful idea. And like I said, the pi calculus is this way to kind of articulate how do concurrent processes work and interact with one another. So it has these three main sorts of operations. You can see it has this sort of theoretical syntax defined up here, which is a bit hard to read, but it has this operation of sending and receiving, where we can have two different processes send and exchange information between one another. We have this sort of random choice operator, where a process can randomly choose with equal probability between two choices. But once it chooses one of those choices, all the information about the other choice gets lost to it. And it also has this replication operator, which basically allows it to continually spawn new versions of whatever process it's replicating. So one of the first things I wanted to do was sort of take this difficult to read syntax and make it something a bit more intuitive. So because the Wolfram language is symbolic, I can just type whatever I want the new syntax to be and create some functions to understand that. So this is the syntax I chose. It's a lot easier to read, as you can see. It just talks about something being sent along a channel, some piece of information X being sent along channel Z, and there's a similar operation for receiving. And then for a choice operator, I just used the sort of double pipe, which usually means or in programming languages, to represent the idea that we have one or another choice. And then a replication is just denoted by surrounding a whole expression in a replicate. So like I could surround all of process one in a replication, and that would continue to make more and more process ones forever and ever. So yeah, that's the basic gist of the pi calculus. And so the next part of my project was, now that I've articulated the syntax, how can I actually write programs in it? And again, the Wolfram language is really great to use here because of its powerful pattern matching. So I can just take the syntax and do a bunch of pattern matching to select which parts of it I want to use, and then I can build a really simple interpreter up from that. So the first step is we need to see what processes can be evaluated. You might remember I said earlier that in a concurrent program, we have all these different processes competing to be evaluated. So we need to randomly choose one of them. And this is what this logic does here. It selects processes that start with send operations or replicate operations, because processes don't want to receive off the bat. We can't evaluate. We need something to be sent before we can receive. So we basically pattern match against everything that doesn't receive, and then we do a random choice to choose one of those processes and evaluate it. From there, we take, if it's a send process that we selected, we want to extract all of the information in that process, and we can just do that in a simple association. So like what information is being sent and where is it being sent to? And then we need to see, are there any receiving processes that are trying to receive at the same place our process is sending to? And we can do that with a bunch of pattern matching again. And then finally, if a process does want to receive something, we need to give it whatever data is being sent. So for instance, a process might try to receive some data and send it elsewhere, but until it has that data, it's just using a placeholder to represent the data it's expecting to receive. So we need to replace that placeholder with the actual data. And that is basically all we need to do to evaluate a PyCalculus program. Here's some extra code just for specific edge cases and stuff like that. But with those functions, we can take our two programs from earlier, and then we get this, which is admittedly very hard to read, but it turns out that this is actually a valid way to evaluate the programs from earlier. And here is our program with replicators. And you might notice that I'm only evaluating this program a finite number of steps, because the fact that this program can replicate means that it will never end. It's a non-terminating program. So we can't ever know what it evaluates to, because it'll just keep going on and on forever. So this is pretty cool. We just interpreted PyCalculus programs in a special syntax, but it's really hard to understand what's going on because the output is not very human readable. So what we can do is, if you remember that sort of arcane looking syntax from earlier, that's the actual PyCalculus syntax. We can try to map our syntax back to it. Even though it's harder to read, it's a lot more compact, so it will give us a better idea of what's going on. And again, we can do that with a bunch of pattern matching and rules. So I'm matching all of the individual atoms in my syntax, like the PySend, PyReceive, back to their representations in the actual PyCalculus syntax. And if we do that, we see that our outputs from earlier, which were pretty hard to read, actually turn out to be just these two things. These are the two simpler programs about replication. And this is what they evaluate to. And if we were all to actually crunch the numbers and everything, we'd see out that this is one valid way to evaluate these programs. And I say one valid way because the PyCalculus is actually non-deterministic. Since we have all of these processes competing to be evaluated, they can be evaluated in a different order every time. And we're just randomly selecting that order. But that order does matter. One order might yield a different result than another order. So especially for a program with choice operations like our second program, this is only one of potentially many possible valid outputs for that program. And so we can add a bit more code and get a more visual sense of what's going on. This is showing what each program looks like as it's being reduced. So each of these cubes represents a reduction state of the program. We take our initial program, we select one of the processes and reduce it, we get this state, and we select and reduce it until we get this state, and we can't reduce it anymore. And this is the same thing for our slightly larger program. And then finally for our non-terminating program. And you can notice it's non-terminating because it just keeps growing in size. The information that we need to describe this program is increasing because everything's just continuing to replicate. And in this case, actually, nothing's even being consumed. Everything's just replicating here, but none of these processes are actually being selected to do any computation. And that's just a random choice how it turned out when I ran this command, because like I said earlier, it's a non-deterministic process. And so all of this non-determinism gives a sort of another element to the PyCalculus program, which those visuals are lacking. Because if you remember that reduction where it showed arrows from one program state to another program state, there's actually another hidden arrow there to another possible program state, but we're just leaving that out. And so I kind of wanted to give a more full description of a program by showing all of those arrow states. And something like that is known as multi-way system. It shows all the possible ways we could evaluate from a starting state to an ending state when there are multiple rules we could apply. So in the PyCalculus, there are multiple processes we could choose, and those are our rules. And the order in which we choose them represents one possible way to evaluate the program. But by using a multi-way system, we can visualize all possible permutations of applying those rules. And that gives another dimension to a PyCalculus program that our earlier visuals were sort of lacking. So again, here's a lot of code doing pattern matching and things. But basically now, instead of just randomly choosing one of the processes, we choose all of them, and then we update all of them, and then we form connections so that we update all of their children, and then all of those children until we get a list of all the possible irreducible states we could end up in. And something like this can be very easily graphed, and we get something like this. So this shows the multi-way system graph for our first program, and it turns out that this program is actually deterministic. There is only one sequence of events we could have, and if we hover over the nodes, we see that each of these nodes is a program state, and it renders beneath it. So you can see the program state keeps getting reduced until it's irreducible. There's nothing left. But now our other program with a choice operator is a lot more complex, because you see we start with a program state up here, but then we have this choice operation. It's represented by the sending x along b or sending x along e, if you can see that beneath there. And so that splits up our possibilities, and we split up possibilities again here. And so it turns out that this program can actually have 3 possible states. And that gives us some information we didn't have before. All we were doing before was visualizing the reduction along one of these possible branches, one of these paths. But now we know a lot more about that program and its nature. It actually has 3 possible states. And we can do this for our non-terminating programs as well here. And these get extremely big because at each step they have the choice to replicate, and we can see how they evolve. So that's pretty cool. There's some things to notice about that. The first is this is like snowflake symmetrical pattern, very spiky, all these clusters. And that's all due to the replication, because after each step we can choose to replicate, and after that step we can choose to replicate too. And that creates a sort of symmetry and clustering. And then the small irregularities, like things here or here that aren't perfectly symmetric, are times when instead of replicating, we actually chose to evaluate one of the replicated processes. But very generally, it has this rough sort of symmetry to it. Let me just close this here. Okay. So this was pretty cool. I was really excited when I saw these results. But it's important to realize that we're using 3 pretty arbitrary programs here that I defined earlier. And so we don't know if all of this behavior really generalizes across the whole space of pi calculus programs. So what we need to do is start randomly generating programs and seeing what the multi-way graphs of these programs look like. And so again, we can write some code to do this. Basically what I'm doing is I'm weighting the probabilities of what is the probability of creating a send, what is the probability of creating receive, what's the probability of creating a choice between 2 possibilities or a replication operator. And so again, there's just a bunch of code to do this. And I also am using a specific terminology here to define the size of a pi calculus program. So an m by n pi calculus program is a pi calculus program with m processes, so m things competing to be computed, and each of those processes has n steps in them. So they might have a receiving step, a sending step, all the way until n steps. So using that code from earlier, what we can do is we can generate 10 2x2 programs, pi calculus programs, and then just evolve them in some order. Again, this is only one of many possible evolutions. And we get something like this. So we can see some of them are kind of complex. Like this one takes 4 steps to evaluate, at least in this order. And then some of them are non-trivial or trivial, sorry, or maybe even nonsensical. Like this might not model any useful real world behavior because it doesn't evaluate at all. It's just static, stuck in its starting state. But what's really surprising is that when I just randomly choose a 2x2 process, I get this as its multi-way graph. And so we have to remember this is only 2 processes, each with 2 statements, which you would think would be very simple, but its multi-way graph is very complex. We have diverging behavior, 1 program state splits out to 3, and then all those 3 program states can potentially converge again. So it's really complicated. And we can see if we look at the specific programs, how this is all happening. So we have a choice to send C along A, or we have a second choice to send C along B or B along A, and then it all splits up and then it comes back together, and then there's another splitting here. So it's a very complex geometry that you might not have suspected, especially given it's a very simple program. It can be described in very little information. And it turns out this idea of complexity does generalize. Here's 50 random 2x2 programs, and they're multi-way systems, and they're in most cases much more complex than this one. You have things like this or this, which are 10 to 15 maybe individual program states that it's bouncing between. And of course, you also have really simple things like deterministic state here, or deterministic program, or programs that don't evaluate at all, just like one line, like this one here. And that's because we're randomly sampling the space. So obviously some of them are going to be trivial or nonsensical programs, but by and large, most of these programs are pretty complicated, and we're just randomly searching. So that gives us the idea that on average, many simple programs have complicated multi-way systems, can be reduced in many possible ways. And again, we just do this with a bit of larger programs, 3x3 programs. These graphs get very big. A lot of cool shapes sort of emerge here. Some of them are notably too big to even be rendered because they have so many program states, like at least I think at the very height, up to 10,000 program states. And you can do the same thing with 4x4 programs too. Here are two graphs I thought were especially interesting. So this one here is a 2x2 program, and it's very complicated. You have a starting state, branches out to these states, and they converge and diverge and converge again. And here's another just cool looking multi-way system for a 4x4 program. And so all of these programs I should have mentioned earlier are not including replicators, right? Because then they would be non-terminating. So we can add replication in and then only evaluate it for 5 steps, which is what I'm doing here. And now we start to get that sort of spiky snowflake-like symmetry we were seeing earlier. We get things like this. Again, you see symmetry here, all these really symmetrical configurations. It doesn't always happen, but most of the time it does. And that just gets even bigger and more dense graphs as we up the size of our programs. So things like this, which are pretty cool, just in terms of the shapes themselves, but also the idea that there's so much hidden complexity here. Okay. So, you know, my conclusion isn't. Okay, there we go. So yeah, so just as a recap, all of these ideas, it's a lot of stuff to take in, especially because the pi calculus is slightly esoteric, as I say here. But the pi calculus is basically the lambda calculus for concurrent programs. It's non-deterministic, so we can visualize this non-determinism using multi-way systems. And the key thing to take away is that even simple pi calculus programs we can articulate in relatively little information, have complex multi-way systems. So how I like to think of this is programs can be simple in the first order, but complex in the second order. And what this means is, if you remember back to our 2x2 program from earlier, each of the paths is maybe 3 steps long. So given a 2x2 program, we can probably get to one output in only 3 or 4 steps. But there are many hidden possible 3 or 4 steps that we didn't take when we chose to take that one. So there's a lot of complexity hidden beneath the fact that, yeah, we can evaluate it very easily, but there are many possible routes of evaluation that we may not see when we just randomly choose one. So I found these ideas to be really interesting, and I'm currently trying to work on exploring this a little more. So one thing I want to do is add the entire pi calculus syntax implementation here. I left out certain operators, like there's a scoping mechanism, which I was a little bit confused how that might fit into what I was doing here, so I left it out originally. I also did some explorations, as you might have seen earlier, connecting the pi calculus to Petri nets, which also model concurrency. So I want to look a little bit more into that and the math of it all. And I want to see some of the use cases of modeling things with the pi calculus, because I came across a lot of interesting instances, especially in biology and chemistry, of modeling reactions with the pi calculus. So thank you. I hope you found this talk interesting. And if you'd like to talk to me about these ideas some more, I'd really enjoy it. Thank you.
Great, Rohan. Thank you. It's fascinating. Fascinating stuff. So feel free to put more questions in the chat, and let's just go through a couple of questions that are already there. So have you examined any programs that, no matter the execution order, lead to the same result? So confluence in general, do they stand out in any way?
I haven't. I don't think from those experiments you generated, at least, there's a program where everything, like things can diverge and everything will converge back to the same program state. But I don't see any reason why something like that couldn't exist, because there are programs where certain parts of it will converge back. So I think there definitely could be something where there's like a bunch of diverging and then everything converges back to a single program state, although I didn't observe any of those directly.
That's awesome. And, have you tried measuring the dimension of the program graphs?
No, I did not try that. That would definitely be an interesting thing to do in the future.
That would be a cool further piece of study. Todd asks, is pi calculus Turing complete?
I believe, yes, I believe it is. I think it can actually be implemented in the lambda calculus. Like there's a way to embed the pi calculus in the lambda calculus. And I tried to understand that, but that was a bit beyond me at the time. So I'm not sure of all the details behind it, but yeah, it is Turing complete.
Awesome. Great. Thank you. Wonderful presentation. Great. So our final presentation is Joseph. Joseph also attended our high school summer camp this year and did some project work on chemistry. So Joseph, feel free to share your screen.
My project was about making networks of different chemical reactions. I'm very interested in chemistry. I've been pursuing specifically organic chemistry for a long time now, and I find specifically synthesis to be a very interesting problem. And I noticed that there's a lot of recently added Wolfram chemistry resources that are very powerful, and I was very interested in trying to tap into those resources and also to learn how to use them so that in the future I could apply those if I needed to use it in a workplace setting. And I think that it would be very helpful for in a laboratory to identify a synthesis route automatically. Right now, a lot of the work is manual, and you need to go through and determine whether you need to use this reaction or that reaction in order to get your desired product. With an automated system, you could do it a lot more quickly and efficiently. The first steps that I took in this project involved learning how to use molecule modify. Molecule modify can do a lot of various different important chemistry modifications. It can alter specific atoms, it can alter specific bonds, it can alter stereochemistry, it can generate coordinates, perform geometry modifications, and many more things. But in this project specifically, I was interested in substructure replacement rules. Here you can see one example of a substructure replacement rule that I made. I don't believe that this has a corollary with an actual reaction, but here I'm replacing a sulfonyl group with a nitro group. A big part of my project was getting molecule canonization to work. Canonization takes multiple molecules that are enumerated differently but have the same structure and changes the ordering of the atoms around such that the two molecules are recognized as equal. The way that Wolfram stores molecules, the various different atoms in those molecules can be numbered in different ways, and those molecules won't be registered as equal, which presents a lot of problems for trying to, for example, generate things with nest graph. If you have two different molecules that are generated differently, they can end up with different atom numberings, and this means that the two nodes will be separate when they should be the same. And this was a really difficult problem for my project. Thankfully, I got some very critical help early on in my project. I managed to reach out to the Wolfram chemistry team, and they found a very clever solution. There's an existing molecule property called canonical smiles, which will take a molecule and it will return a canonical smile string, which is a manner of encoding that molecule through text. And then I can re-input that back in as a molecule, and that will canonize the molecule for me. The first application that I did with Molecule Modify was making an alkane network. Alkanes are the simplest type of hydrocarbon, which just involve, of course, carbon and hydrogen, and they don't have any rings or double or triple bonds. And what I would do is, rather than using replace substructure, for this I use replace substructure list, because with replace substructure, you would take every viable substructure, every matched substructure, and replace it with a new substructure. But with replace substructure list, you find each substructure, and then you compile a list where each substructure is replaced one at a time. And by using this, I could gradually replace each unique hydrogen with a methyl group, and then I can canonize the molecule on each step to make sure that the graph will merge back together when the molecule is identical to another molecule. Something that's particularly important here is explicit versus implicit hydrogens. In order to store the molecules a little bit more efficiently, Wolfram will do what's called implicit hydrogen conversion, where it would take a molecule and scrub off all of the hydrogens which are bonded to carbon or nitrogen or an oxygen maybe, and it would just re-implement those when it drew the molecule, but it wouldn't actually have those stored in the molecule data structure. They'd just be re-implemented. So I needed to make sure that on every step, my hydrogens remained explicit, because the replace substructure would make them implicit again in order to save on data. And here we can see the molecule gradually grows, and it also branches off. For example, here we have butane versus isobutane, and this graph will gradually grow over time. At this point in my project, I decided to shift focus to performing chemical reactions, or the best approximation I could with molecule modify. A lot of reactions have specific instances where they will mess up the reaction or do possibly worse things, like they could result in an explosion if you mix the wrong chemicals. So in a laboratory, you need to make certain checks for incompatible reactions, but with molecule modify, this can be a little bit difficult. However, I still think that the graph that I got is mostly accurate and has significant data that we can garner from it. Here I have one example of a graphite generated. This is centered around 1-butene. I decided to choose 1-butene because a lot of my reaction set is focused around transformations on triple bonds. So by starting with a molecule with a triple bond, I could generate a lot of unique molecules. And here I also have loaded in a slightly larger reaction network. It grows quite quickly, so it's a little bit difficult to go much further past this size. So the next step of my project was to visualize all of this data. One example that I have here is a visualization by atomic mass. I decided to color it in, and I think it looks quite nice, but also one important thing that this tells us is we can notice that the lighter weight molecules tend to have more connections than the heavier weight molecules. And I think that's because with my reactions that I implemented, the lighter weight functional groups had more viable reactions than the heavier weight functional groups. So heavier weight functional groups didn't have the same opportunity that lightweight functional groups did in order for them to generate new molecules. And here I have a similar graph, but instead it's representing the number of connections at each node. And you can identify a couple molecules that are specifically strongly generating for a number of other molecules in the graph. Particularly here are a couple with brominated sites, those are targeted by my various reactions in my reaction set, as well as multiple bonds on carbons. Here I have what I call a reaction cascade, where I used a layered digraph embedding with the top node as 1-butene. You can tell from the lengths of some of these edges that it's not exactly sequential. Doing so would make it expand out wide too far. So it compresses it a little bit in order to make it a little bit more readable. But I still think that it gives a helpful way of seeing which chemicals can be produced in fewer steps and which chemicals take a couple more steps in order for them to be synthesized. And here I have a graph of the percent carbon mass by the percent hydrogen mass. Along here I have the hydrocarbon line, where the percent carbon and percent hydrogen add up to 100%. I have a substantial gap here because I don't have many functional groups that are substantially lightweight compared to the mass of the molecule. If I had larger molecules I was working with, this area would be more populated. Then descending down, most of the functional groups here are oxygen and nitrogen-based functional groups, and they tend to add more oxygens and more nitrogens as it moves closer to the origin. Then I have a lot of functional groups that are sulfur and chlorine based. These functional groups tend to be a little bit heavier. Then down here, they become more bromine based. I have a lot of molecules with bromines on them down here because bromine is quite a heavy element. And at the bottom, most of the molecules down here are what's known as Grignard reagents, which are a type of organometallic molecule, which have a functional group that is magnesium bromide. The magnesium bromide functional group is particularly heavy, which makes these molecules especially far down on my graph. In this project, I ran into a couple limitations with molecule modifying reaction networks. Molecule modify doesn't have a lot of capability for reactions with chiral molecules, especially reactions that see an inversion of chirality. So I'm hoping that I'll be able to remedy this with some of the more recent, some additions to the Wolfram chemistry resources that should hopefully be coming out soon, like new types of bonds. I have a difficult time using molecule modified to distinguish steric hindrance and its effects on reaction favorability. Certain reactions are more favorable with more sterically hindered molecules, that is, molecules that can't move around as quickly because they're made out of heavier things. And some reactions prefer lighter molecules that can move faster. And this can cause a really big effect on which molecule can be easily isolated from a reaction and which molecule you really can't make a certain way. Additionally, this plays into the reaction rates issue. I can't really get a clear picture of how quickly any of these reactions would proceed. I like to try and see if I can do energetic simulations in order to determine how quickly a given reaction would proceed. Additionally, I don't currently have the capability to do reactions with multiple organic molecules, like reactions that combine two molecules or reactions that split apart a molecule into two parts that can each be isolated by themselves. I do expect that with a little help from Petri nets, I'd be able to do that, but I'm not sure. I don't believe Wolfram currently has a nest Petri net function similar to its nest graph function. And lastly, I can only really use a pre-coded reaction set. So finding novel reactions becomes a lot more complicated. That would require using mechanistic calculation, which I'm looking into working on.
Awesome. Thanks so much, Joseph. Very cool. Great. If anyone has any questions, feel free to put them in the chat. Let's see. We have Joseph, could you use this tool to create a metric for molecule similarity through the number of changes required getting from one to the other?
Yeah, you could definitely find at least a partial metric for molecule reaction similarity, how close two molecules are in reaction space. But some molecules might not be interconvertible, and there's a lot of factors you need to consider with what reagents you're using and how that affects the distance. So you'd likely need to implement another metric on top of that in order to provide reliable data.
Sweet. It's been commented that all of these projects are very high level and on par or better to many adult summer camp programs. So we should be very proud of you, which we are. Awesome. So I'll let anybody type out any more questions that they have specifically for Joseph about his project. So any questions about becoming a mentor at camp? We look for adults, undergraduate students all the way through, our retirees. I think we have great success with more senior mentors as well as younger ones. Can you guys hear me properly?
You lied out a little bit there, but you're back now.
Okay, cool. So I was saying that yeah, there's a really bad storm here right now. So if I go out, I'll have to go onto a hotspot. But yeah, so I was saying that this is a great opportunity to ask any questions that you have about camp, about sending your kid or your student, or coming to be a mentor yourself at camp. And yeah, we'd be really excited to hear any questions or talk about camp for you. It seems like extraordinary new patterns could be discovered with your work. Do you have any kind of overarching theories that you're working on?
I mean, I don't know if I'd call it a theory. One thing, like I mentioned, I wasn't really able to get to was sort of the relationship between the pi calculus and Petri nets, which I think Joseph also mentioned Petri nets, but it kind of what we kind of got a sense of, like also when I was working with my mentor and stuff, is that there's sort of a way to map between the pi calculus and Petri nets as different ways to model concurrency, which we kind of have an intuitive understanding of a little bit, but like not a really super very like mathematical understanding of that. So that's something I'm currently working on with the help of some people at Wolfram Research to try and understand a bit more. But yeah, I think that's like the main next direction I'd like to take this project, trying to explore a lot of that relationship more.
I think that my area of focus at this point is going to be primarily on mechanistic approaches to finding molecule transformations. I've been trying to get a way to do atom by atom cumulative transformations that would eventually result in an entire reaction completing, but I didn't get very far on that, and I'm looking forward to some new improvements in Wolfram version 13 that I think might help a little bit with that.
Cool. Yeah. That for a second, we're good. Fiona, do you think your program could be used for determining plant health, for example, for agricultural use?
So I haven't done enough research to know if the anther is directly related to the health of a plant, but I think if so, then yeah, I probably would be able to.
That's awesome. Very, very cool. Fiona, what was your favorite part of camp?
The middle or high school?
Let's talk about high school.
High school, I think it'd probably be how we bonded after doing like the work. So during the camp, we had like work sessions where we would be able to individually work in our own groups with our mentors. And then after that, we'd have like small stretch breaks, and like we'd also be able to like just have small breaks. So I think those were good times where we had time to bond.
Totally. Totally.
The stretch breaks were a real lifesaver there.
Yeah, being stuck on Zoom is a sad state of affairs.
I also really enjoyed Chicken Scratch. I don't remember his name, but somebody brought in a game called Chicken Scratch, which is it was like an automated trivia competition game, which would help people get better with trivia, and it was really fun. We had a good time with that one.
Great. Rohan, favorite part of camp?
Yeah, I guess I just add on to both Joseph and Fiona. All of the like cool social activities we did were really fun. Also, I guess more on like the work side, it was kind of interesting to see like all the mentors presented a lecture kind of relating to their own expertise in work. So like since the Wolfram language is like so big and there's so many areas in it, when you like choose your project, you sometimes get stuck in that area and you maybe don't really know about all the stuff you can do outside of that. So like for me, that was a cool way to like see things other than what I was working on and like learn a bit more about parts that I didn't really know that much about. So that was also pretty cool watching the mentors give their lectures.
I agree. I really like that bit too. So all of our mentors give a kind of 30 to 60 minute presentation on like something cool that they've done in Wolfram. And because all of our mentors are themselves cool, we always get a really wide variety of awesome stuff that's done. So I think this year we had everything from like computational art to like using Pokemon entities to make Pokemon cards, and we had some like astrophysics stuff and some computational geology, all kinds of really wide range of stuff to like expose you to all these cool things. Awesome. Great. Joseph.
I really feel like the Wolfram Summer Camp gave me a lot of very, very helpful academic options, especially with Wolfram, that I would not have had otherwise. And it was a very enjoyable camp. And I'm going to be working with people at Wolfram for likely long into the future now.
Awesome. Great. And Fiona?
And yeah, I also wanted to say that the mentor lectures were really cool, and they introduced me to like a wide variety of topics that like at school they haven't taught me about before. So they were really cool.
It's awesome. Yeah, I think it's really cool how you get so much like exposure to different things and like get to meet some cool grown-ups, and I think I love camp, but maybe I'm biased because I made it up. But yeah, okay, so in our final kind of 2 minutes, I just want to stress to everybody here that if you're interested in becoming a mentor at camp, or interested in sending any of your students, if you're connected to students, or sending any of your children, if you happen to have kind of 11 to 17-year-old children to any of our programs, then please message me on Pathable, or feel free to email me, and I'll make sure that my email goes in relevant places. So for example, it's about to go in the Pathable chat. So feel free to email me with anything that you might think about camp. And Joseph?
Should we post our computational essays somewhere?
Yeah, that would be great. Yes, so yeah, if you're interested in reading more about any of these students' projects, they've all written computational essays, which are on Wolfram Community. So I'll make sure that all of those go in the description of this meeting in Pathable, so you can go check those out. And if not, then they're also on the community website.
Also, go check out other students.
Absolutely.
Computational essays, they're all listed under the Wolfram Summer Camp tags, and specifically the 2021 tag for our year.
Yeah, amazing. Yeah, everybody did some really cool projects. Okay, thank you so much, Fiona, Rohan, and Joseph, for presenting your projects. This was really exciting. You've had a lot of comments in the chat about how kind of high level and interesting and amazing these projects are. So you should be very proud of yourselves. So, thank you everyone for coming. I hope you all have a wonderful rest of your day, and we'll talk to you real soon. Enjoy the rest of the conference. Thanks. Goodbye.